As we're taking a look at the traffic patterns in our network, we might see that traffic falls under one of three main categories. The first category is Unicast. Unicast is a one-to-one communication. In other words, you've got one device, like your PC, talking to one other device, maybe a host on the internet, or you're printing to a printer. It's a one-to-one communication. Contrast that with broadcast. A broadcast is a one-to-all communication. Well, at least all within a subnet. I could do a local broadcast to an address of 255.255.255.255, and that would go everywhere in my local subnet. Or I could do a directed broadcast. I could specify a network address, but I could then set all the host bits in that network address to a 1, and that's going to be a directed broadcast. That's going to go to all devices in another subnet. And finally, we have multicast traffic. Again, unicast, that was one-to-one. Broadcast was one-to-all. Multicast is one-to-many, or potentially many. With multicast, we send traffic out. The multicast source is sending traffic destined for a Class D IP address. And that Class D IP address, we're going to call that a multicast group. And devices that want to receive that multicast traffic, like your PC, it can join the multicast group, and all of the members, all the devices that have joined the multicast group, they can then receive that transmission going out to that multicast, to that Class D IP address. Unicast might be the simplest type of traffic flow to understand. It's a flow, it's a conversation between just two parties. I'm sending from one source to one destination. For example, in this case, we've got a video server, and let's pretend that we have three devices on the network, three hosts at IP addresses of 10.1.1.1, 10.1.1.2, and 10.1.1.3, and let's pretend that the first two, 10.1.1.1 and 10.1.1.2, they do want to receive video from this video server. And with Unicast, here's how it would work. The video server would send a packet destined for 10.1.1.1, and it would go just to that host. And then it would send another packet, and that other packet would be destined for 10.1.1.2, and it would go just to that host. There is a benefit to this approach. 10.1.1.3 did not have to see any unwanted traffic. It didn't have to deal with those unwanted video packets. A downside to that approach, though, was that video server had to work almost twice as hard. It had to send each packet twice. And we only had two receivers in this case, but what if we had 100 devices that wanted to receive this video stream? The same video frame, the same packet, would have to be sent out 100 times. And that could start to impact not just the processor of the server, it could start to impact the bandwidth on that server's network link. So Unicast is very appropriate sometimes when I'm sending a print job to a network printer. Obviously, only my device and the printer need to be involved in that conversation, but if we want to send from something like a video server out to multiple recipients, Unicast might not be the way to go. Another type of traffic flow we have a great deal in our networks today is broadcast traffic. Broadcast traffic is sent from a source and it goes to all of our IP addresses on a subnet. It might be our local subnet. It might be a remote subnet. If I'm sending to my local subnet, notice what happens. If I'm wanting to send a video out to the top two computers on screen, 10.1.1.1 and 10.1.1.2, if I broadcast each frame from the video server, watch what happens. The destination address is all 255s and it goes everywhere. The good news is that's less of a processor burden on the video server as compared to the Unicast model. It's lower network utilization on that video server's network link as compared to the Unicast model, but on the downside, everybody in the subnet saw this broadcast. It went to 10.1.1.3, which had to take a moment, look at the packet, realize that's not for me, and discard it, but it was interrupting 10.1.1.3, so that's not a great solution either. Some network traffic, though, does need to be sent as a broadcast. For example, if my computer is trying to properly form a frame, to send to another computer, and I know that other computer's IP address, but I don't know the other computer's MAC address, I can send a broadcast. Specifically, it's called an ARP, an Address Resolution Protocol broadcast, to say, hey, does anybody know the MAC address of this IP address? You see, I don't know who to send it to. I'm just broadcasting it out, hoping somebody will reply. There are many times when it is appropriate to send a broadcast packet. And the example on screen with a destination IP address of 255.255.255.255, that's going to be a broadcast on our subnet, but we could specify a directed broadcast address. This is where we specify that remote network address with ones. A binary 1 is going to be in the position of each of our host bits. If all the host bits are set to 1 and all the network bits are set to whatever network we're targeting, that's a directed broadcast address. For example, I might send a directed broadcast to 192.168.1.255, and that's going to go to all the hosts in the 192.168.1.0/24 network. So we've got broadcasts on our network, and we've got directed broadcasts. When we talked about Unicast, that was a one-to-one communication. Broadcast was a one-to-all, at least all devices within a subnet. Here we're taking a look at multicast. Multicast can be thought of as a one-to-many traffic pattern. For example, going back to our scenario where we had 10.1.1.1 and 10.1.1.2 both wanting to receive this video stream and 10.1.1.3 not wanting to receive it, that's a great example of where we could use multicast. What we could do is have the two receivers, the two devices that do want to receive the traffic, they could join a multicast group. And a multicast group is going to have a Class D IP address. Do you remember the range in the first octet of Class D IP addresses? It was 224 through 239. And generally, within an organization, we use 239 in that first octet for use inside of our organization. And here we have a multicast group of 239.1.2.3. And both of these PCs, 10.1.1.1, 10.1.1.2, they have both joined this multicast group. Now, the video server is going to be sending a packet, and the packet is destined for, it has a destination IP address of 239.1.2.3. It's destined for that multicast group. Did you notice what happened in the animation? Only the intended recipients got the packets. The non-receiver didn't have to deal with it. And for an application like this, that's a great compromise between Unicast and broadcast. Remember, with Unicast, the server had to send 2 copies of everything, one for each destination. The good news was that the non-receiver did not have to deal with the traffic, but it was a higher processor burden on the server. It was a higher utilization on the server's network link. And with broadcast, we only had to send the traffic once, but it went everywhere within a subnet. Now we've got this compromise of multicast. With multicast, we only had to send each video packet once, just like broadcast, and only the intended recipients got the traffic, just like Unicast.